Hello guys. Okay, so welcome to our next discussion on functions. And today we are going to look at uh, one of the most common categories of functions, which the injective, surjective, and bijective functions. You see that? So functions that we always deal with can always be put under one of these categories. You see that? So now we're going to understand what it means or what determines what is it that determines that a function is going to be contained within the first category or the second or the last one. You see, so we're going to present definitions of all these different types of functions that are mentioned here. Okay, so let's start with an injective function. So what does it mean to say a function is injective? You see, so a function f which maps A to B is said to be injective or an injection if f of A1 equal to f of A2 implies A1 is equal to A2 for all A1, A2 elements of A, like that. You see. So we say a function is injective every time when it satisfies this condition. That is, if you first suppose that f of A1 is equal to f of A2, then it leads to the implication that A1 is equal to A2 for all elements A1 and A2 which belong to A. Or f from A to B is injective if A1 not equal to A2 implies f of A1 is not equal to f of A2 for all A1, A2 elements of A, like that. Easy. So we say a function is injective when either one of these definitions hold true. You see that? So when either one of these definitions hold true, then we say the function is injective. You see? So those are things that you should know when it comes to function, to know these different classifications of functions that we have in this area. And also you must be able to apply these definitions most of the time when it comes to problem solving. So what we're going to do now is we're going to look at a typical example on what can be asked under such definition, you see. But let's first give that no. If you look at previous lesson that we made, which was the elementary discussion of functions, we did show a diagrammatic visualization of what it means actually to say a function is injective or an injection. So I'm not gonna redo it here. If you want to, you can just go back to rewatch the video. You see. So now what we're gonna look at is the following result. So we have the following theorem that is worth stating at this moment, you see. So the function f from R to R such that f of x is equal to mx plus c, with m c element of real numbers is injective. You see, so one of the things that you should always know is that a function which is linear, like the one shown here, is an injective function. So how can we prove this? So the proof of this result is quite simple. So we'll say, suppose A1 and A2 are elements of real numbers. So let's suppose that A1 and A2 are just some elements. And then suppose also that f of A1 is equals to f of A2. So let's suppose these two statements. You see. So let's say we have all that. So let's suppose that this is true. So if this is true, what does it mean? It means that MA1 plus C is equals to MA2 plus C. So these cancels. So we can see it follows that MA1 is equals to MA2. So finally, we have that M bracket A1 minus A2 is equals to 0. So we have a product of two things is equal to 0, but we know that M is just arbitrary. You see that? So this M is just an arbitrary real number. So if this result is to be true for any arbitrary real number, it then follows that A1 and A2 might be the same. You see? So therefore, F is an injection. You see that? So therefore, it follows that this function F is an injection, just as we have seen here. So it is always good to make sure that you know how to deal with all this. So also another theorem. So I'll call this theorem 2. Then I'll just list a lot of facts, but at the same time. So the function f of x defined by a dot b to x plus q with a, b, c element of real numbers such that a is never equal to 0 and b is not equal to 1 and b is greater than 0. If so, the function f of x with that and that is injective. You see, so one thing that you should know is that the exponential function defined that way is an injective function. Then b, the other thing that you should know again is that the function f of x, which is defined as a over bx plus c plus q with a, b, c, q elements of real numbers is injective in its domain. So these functions that we have just stated here, they are functions that are very easy to prove that they're actually injective functions. You see, so that function that you see there, it is an injective function and it is always injective, this one in its domain. So the proof of these, I'm not going to waste time doing them. So you can just do as practice. So you can do those ones as practice. I'm not going to bother waste time trying to prove to you that these functions are injective. So these are functions that you can readily see even by inspection that they are indeed injective, but it will be good to use the same line of reasoning as we demonstrated here to show that these functions are indeed injective. You see. Then now let's move on to the discussion of surjectivity. So surjective function. So now, what is a surjective function? You see, so the function f, which maps A to B, is said to be surjective. So the function f, which maps A to B, is said to be surjective if for all B elements of B, they exist an element A in A such that f of A is equals to B. You see? So that's what we mean by saying a function is surjective. So this is how we define surjectivity to mean. So also the diagrammatic visualization, I'm not going to bother here. What it simply means is that when you pick any element in the range, you can always find an element which is assigned to that particular element in the set A. So that's what surjectivity means, you see. So we say a function f is surjective if this is the case, like that, you see. So this is one of the trickier things to verify with functions. So what I'm going to do now is we're going to look at examples where we actually prove subjectivity of different types of functions, you see. So one of the examples that we're going to do in this particular problem will be as follows. So the first example, which I could have also stated as a theorem, is as follows. So prove that the function f of x equals to mx plus c with both m and c elements of real numbers is surjective for all x element of real numbers. You see, so prove that this function is surjective. So how does one prove that a function is surjective? You see, so this can be a very tricky proof to do mostly in math, but we're going to demonstrate here how to actually prove that this is indeed true. So how can we prove that a function such as that one is surjective? So the proof of this, it goes as follows. So what we're going to do first is we're going to pay attention to the definition of subjectivity. So let's go back and recall the definition. You see that if you want to prove subjectivity, you have to take any element that belongs to the range, and then you show that for that particular element, there must exist something in the domain that is assigned to that. So which means I'm going to follow the same spirit here. I'm going to take any element that lies in the range. So I'll say, let beta be an element of the range of f. That's what I'm going to say. So I'll say let beta be an element which lies inside the range of f. You see? Then now we need to prove that they exist an element alpha which resides also in the real numbers such that f of alpha is equals to beta. You see, so now that's what we have to prove. So we have taken a beta element which lives inside the range. So remember this range that we're actually talking about here, this guy is just none other than the real numbers. You see, so now I want to show that for any real number that I can pick, which is in the range of the function f, they exist something in the domain which maps to that particular element. So now how do we go about that? So to do these kind of proofs, what you have to do is to show that there is a way of constructing an alpha that will give you beta when you substitute it into the function. So what I will do now is I'll say, let's define alpha is follows. So let's define alpha to be beta minus n all over m. So let's define alpha that way. So now what we have. So if we define alpha this way, what do we see now? What is f of alpha? So f of alpha is m because alpha is mx. So it's m times beta minus n over m, then plus n. So we see the m and m cancel, so we revert with beta minus n plus n, which gives us the beta. So therefore, we see that this is true for any beta, the existent alpha. So therefore, the function f is surjective. You see, so the function f that we have here is a surjective function. So this is how one can verify that, yes, indeed, a function such as that one is surjective. So another example 2 that can be asked is as follows. So prove that the function f of x equals to a over, let me not complicate things this time. Let's just say x minus p, then plus q with a, p, q element of real numbers such that a is not equal to 0. So like that. So prove that the function, this one, with AP satisfying all these conditions is surjective. Wherever is defined. So wherever this function is defined, prove that this thing is surjective. So now how can we prove that such a function is surjective? So now we know the whole trick behind it. So what is the proof? So at first we say let beta be an element of the range of the function f. So whatever the range is, beta will come from there. Then we will prove that they exist in alpha, which is an element of the domain of f, such that f of alpha is equals to beta. So that's what we're going to do now. So we'll take that thing and we're going to show now that for this beta that we have chosen, they exist some alpha, which can get the job done. So how can we define the alpha in this case? See, how can we define the alpha in this case? So now to define the alpha, I will define alpha as follows. So let's define alpha equal to what? So we define alpha to be beta minus q over a, then we add plus p inside of it. So we define alpha to be that. Now what is f of alpha? So now let's calculate what f of alpha is. So now what is f of alpha? So according to the definition, f of alpha is a over alpha minus p plus q, which is equals to a, where alpha is b minus q over a plus p, then minus p, then plus q, like this, because this whole thing here was just alpha. So alpha has been replaced with that. So we can see now that the p and minus p, they cancel. And then what happens? Sorry. I think I made a mistake here because this is not gonna actually give us what we need. It was supposed to rotate here. Sorry about that. So I'm supposed to actually rotate this so that it becomes A over beta minus Q. Yeah. Then, sorry, what am I writing here? Confusing myself. So alpha, the definition of alpha is not supposed to be this one here. It's supposed to be A here over beta minus Q here. Then now f of alpha is going to be A over beta minus Q, then plus P, then minus P, then plus Q, like that. Yeah. Then now these two guys cancel, and then A is divided by that. It's same as saying A times beta minus Q over A plus Q. So we see A cancels A, and you remain with beta minus Q plus Q, which gives us beta. So we can now see that yes, there is such an alpha that exists. So therefore, f of x, or just f, is a surjection. You see. So for good practice, it would be good to just to do this one. So prove that. So prove that a f of x, which is defined as a dot b to x plus q with a b q element of real numbers such that a is not equal to 0 and b is greater than 0, but at the same time b not equal to 1. So prove that this function like that with so prove that this function with these conditions supplied on it is surjective. You see, so to prove that a function like this one with all these conditions applied to it is a surjective function. So you can do that as practice. I'm not gonna do that uh, at this point in time. Then, before we finish, it will be good before we end this lesson to actually put the following theorem. Let's see. So theorem. So let f from A to B and G from B to C be functions. So let's suppose f and g are functions like that. Then the following conditions hold true. You see that? So if f and g are injective functions, then the composition of them, which is g o f, is also injective. Then B, if f and G are surjective functions, then the composition again G of F is surjective. You see. So these are things that you should know. That every time when your functions, these conditions hold true, the composition of injective functions will always result in an injective function, and the composition of surjective function is a surjective function. So which means injectivity and surjectivity are preserved properties. You see that. So when you take a space which only consists of injective function, any composition that you do will always result in injective function. So which means this property is preserved uh, in a space most of the time. So that is the same with the surjectivity of functions. So now what you want is to actually prove. So I'm going to prove the first one, and the same logic can be applied to the second one. So let's do proof. So do for part A only. So what I'm going to do, I'll say, suppose f and g are injective functions. So let's suppose f and g are injective functions. You see? So let's suppose f and g are injective functions. And suppose also that, and let's suppose also that g of f of some function a1 is equal to g of f of some function a2, with both these a1 and a2 elements in A. You see, so suppose this is true. So if this is true, then what? So we can see now that this implies G of f of A1 is equals to G of f of A2. You see that? But now when you look here on the left-hand side, you have G of something and G of something. So maybe let's call this this thing that we have here as some alpha 1 element, and let's call this here as some alpha 2 element. So which means in this case you have G of alpha 1 being equal to G of some alpha 2, and we know that G is injective. So if G is injective, then it must follow that alpha 1 and alpha 2 are the same. You see that? Because that's what we mean by injectivity. That if G evaluated at another point is equal to G at some particular point, those 2 points must be the same. You see? So this implies then from here one can deduce that f of A1 is equal to f of A2. So we can write that G is injective. You see, like that. So this implies that. But now we have f of A1 being equal to f of A2, and we know that f is also injective. So this implies, again, A1 is equals to A2. So this conclusion follows from the fact that f is injective. You see. So therefore, what do we see? So therefore, GOF of A1 equal to GOF of A2 implies A1 is equal to A2, and thus the function GOF is injective. You see. So those are things that you must make sure that you understand when it comes to this whole idea of functions. You see. So yeah, that's it about some properties of subjectivity and injectivity. But now it will be worth also then defining what bijective function is. So what is a bijective function? So a function f which maps A onto some set B is said to be bijective if f is injective and surjective at the same time. So if it's always the case that these two are both injective and surjective at the same time, then this follows, you see. So that's what we have to know when it comes to surjectivity, that bijectivity, that a function, when we say a function is bijective, it means it is both uh, injective and surjective as at the same time. So those are things that you should know. Then I also forgot to mention something, you see. So this is something that was worth mentioning when we're defining this function. So a function which is surjective most of the time, we also say it is an onto function, you see. So when a function we say it's onto, it means it is surjective. And then a function which is injective, like the one, it is one-to-one. So if a function is injective, we mean there is a one-to-one correspondence. And a function which is surjective, some folks, they say the function is onto. So onto simply means surjectivity. So yeah, that's the other thing that I can add. Otherwise, yeah, that's it for today. We are going to end it here. So thanks for watching. I'll see you next time on